Hello everyone, my name is Andrey, today we can see learning Python, and today we'll work with an algorithm that created us more than $2 trillion. So let's start. I'm pretty sure you're interested, and that algorithm is called... Let's answer some questions. So we're gonna have 3 questions. What's that algorithm? How did it create $2 trillion? And how does it work? After that, after we answer 3 of those questions, we're gonna write that algorithm ourselves. It's not gonna take up more than 20-30 lines of code, but that algorithm really created more than $2 trillion. And I'm pretty sure in the future that value will continue growing. It's called proof of work. Proof of work. It's an algorithm that is used in Bitcoin and Ethereum right now. So 2 major cryptocurrencies, and if we compare all of the market capitalization stats on all of the cryptocurrencies, it will add up to like $1.8 trillion, but in the past it was more than $2 trillion. So proof of work really created $2 trillion in value. But how did it create it, what it does in Bitcoin and Ethereum, and how does it actually work? When we send transactions in Ethereum, in Bitcoin, we need to validate those transactions. Because if I don't have enough money to send that money, for example, to you, that transaction is invalid, and I can't really send that money to you because I don't have it. In order to validate transactions, we're going to run proof of work, and we are already running it. We run proof of work that allows us to check that. All right, that block is valid. Let's add it to the blockchain in very simple terms. And proof of work actually allows us to add blocks to blockchain. All the miners in Bitcoin and Ethereum use proof of work in order to mine new blocks and add them to those cryptocurrencies. But how does it actually work? In order to make proof of work, we need 2 concepts. First of all, we need some kind of job, some kind of work, because it's proof of work. And second of all, we need the proof that that work, that job was executed. So 2 concepts, some work, and it's really important that that work is not specific. So we can't say you did that or you did another thing. Some concept of a work, some concept of job. And then we are going to have our checker, our validity checker. So we're going to have something that can very easily and very quickly check that that work was executed. 2 main concepts, our work and the checker for that work. So that can really prove of work and proof that, I think you know what I mean. So let's implement it with Python, and I'll explain how does it actually work, because those concepts are really vague.
Alright, so how can we actually implement proof of work with a simple Python application? First of all, let's create our function called proof of work, and what I'm gonna have as an argument is some input data. So input data here. Proof of work function will allow us to find the answer to some kind of job, to some kind of work. And how can we actually do that? We're going to use hashing functions or hash functions, whatever you like. I'm going to import hashlib. Hashlib is a library in Python that allows us to use different hash functions, and following the Bitcoin, we're going to use SHA-256. So it's a hashing algorithm that allows us to get an input value. In our case, it's going to be our input data, which is going to be a string. And hashing function is simply a function that returns you some kind of a fixed length string that represents your value, but you can't really tell. So I'll show you, and I think you'll get it. But I really suggest you watching other videos on hash functions if you don't really know what I'm talking about. So let's, for example, give hello here as an argument, and we're gonna encode it to be bytes, because that function SHA-256 allows us only to work with bytes. So we're gonna encode our string because we provide the string here, so UTF-8, and let's run it. As you can see, and the last thing is hex digest. So, alright, so now we can see it. What I did here, I created proof of work function, and I used SHA-256 algorithm in order to encode my input data, which is going to be bytes, so because I use encode here, and I encoded it to be bytes and then hash. So hash and hex digest is just a function that allows you to look at your hash in that form. So there are different forms. You can look at zeros and ones, you can look at just hashing objects and all that stuff, but we're gonna need that form. So simple hex digest form. So what we did here is we got our hash. So for hello, hash is gonna be that. For hello2, hash is going to be completely different. So the only idea of hashing function is that we have some input data, we give it to the method, and then that method returns us a hashing string. So all of those are fixed length strings. Even if I run my program with that string with lots of data, I can do whatever I want, but still the string itself is going to be a very fixed return that, yeah, it's going to be a fixed length. In our case, it's going to be 256 bytes long, and it's going to allow us to really execute proof of work in our Python application. But how does it actually work? So we have our hashing function, and it returns us a value that represents that string as a SHA-256 hash. It's really easy to get the hash from an input value, but it's really hard to get an input value from a hash. So it's basically impossible. We can do that, but it's going to take us more than 500 years, and it's not worth it. So that's the main idea. It's really hard to get the input value from a hash, but it's really easy to get hash from an input value. That's it. So now let's imagine that we have some input value like Andrew, or Andrew, like that. And what we're going to do here is we're going to have something called nonce. So nonce is a value, a random value. It can be a string, it can be a list of objects, but most of the times it's just a number. So nonce, number that is only used once, and that number is going to be added to our input data. So I'm going to create an f string here, which is going to have input data and then nonce inside. So we just basically put, in our case, Andrew and 0. It's going to be Andrew 0 as our initial data to that SHA-256 function. And now let's look at the returns. So return, as you can see, that is the first hash. So hash with Andrew 0 gives us that. If I change nonce to 1, it's going to give us completely different hash. And we can't really tell what's the input for the first hash, what's the input for the second hash, because once again, it's really easy to get the hash from the input data, but it's really hard to get the input data from the hash. Alright, and now the most interesting part. We need to execute some kind of work. And in order to do that, we can use hashes. What we're going to do is have some kind of symbol combination that will allow us to really understand that that work was done. For example, we can start with 5 zeros at the end of, we can start with 5 zeros, yeah, we can start with 5 zeros, we can start with A, B, C, D, E. So we have some kind of a characteristic that allows us to really show that that work was done. In our case, imagine that we start with 0, 0, so 0, 0, 0, 0, 0, like that. So we have 5 zeros and then our hash goes on. And that is how it actually works. So we have some kind of a characteristic that shows us that that work was done. What's most important is that we can't reverse our hashes. So we can't really cheat and just put a bunch of zeros and then put some random data here, because it will not add up. We have our input and we have our nonce. And if I'm going to run my input, so my Andrew and nonce as 0, I'm not going to receive a hash that has 4 zeros or 5 zeros at the start. Once again, it can be anything. It can be A, B, C, D, E at the start of our string, at the end of our string, in the middle of that string. We have some kind of a characteristic. And the only way to really get that hash that allows us to really, in order to get that hash, what you need to do is actually get all the nonces from 0 to infinity that will start with 0, 0, 0 at the start. So it may sound very complicated, but I'll actually show you what is the algorithm itself. So we have hash value, we hash our string, and what I'm gonna say, while not hash value starts with 0, 0, 0, 0, let's go with 4 zeros in the start. So while our string does not start with 4 zeros while our string does not have 4 zeros at the start of it, we're gonna do the next thing. We're gonna copy that, put it here, change our nonce, we're gonna add 1, and compute the hash value again. So what we are basically doing, we have some kind of work once again, and we need to check that that work was done. That is work. So that is work. Computing hashes is our direct work. And in order to do that, we have nonce. And we have some kind of a unique characteristic that shows that that work was done. In most of the cases, those are leading zeros. So 0, 0, 0 at the start of our hash value. If we don't have that characteristic, that unique characteristic in our hash, what we're going to do is change our nonce, because each different nonce values give out different hashes, and we don't know what the hash will be until we really just compute it, because we can't reverse the hash. So the only way to get the hash and check for that unique characteristic, is to really just pick a random nonce and compute that hash. So we change our nonce and compute the hash again. If it starts with 4 zeros, we just end our loop, and in our case we're gonna return our hash value. But if it does not start with 4 zeros, what we're gonna do is continue looking for that hash which has that unique characteristic in the hash. So it can be at the start, at the end, wherever. And let's just actually print our nonce and hash value, like that, hash value and nonce. Let's run proof of work and you see what is the result. So as you can see, we iterate through all of the nonces, through all of the hashes, and none of those give us the 0000 at the start. So we've gone from 0 to 63,028 nonce, and that nonce gave out that hash, which started with 4 zeros. And basically what we did here is we executed some kind of work, because we computed our hashes. In our case, once again, we did that work. We computed all the hashes, and now, after that, we can return not hash value, but nonce. So nonce is the answer for our problem. Nonce is the answer. What is the proof of work for Andrew, for that input? It's going to be Andrew and 63,028 as a number. Alright, now the only thing that is left to do is to check that our proof of work really works. We really execute some kind of work. And in order to do that, we're going to have a new function called check proof of work. It's going to have input data and nonce as arguments. And what we're going to do here is basically I'm going to copy that line and I'm going to return that line, and starts with at the end, like that. Then I'm going to print is valid, and let's check proof of work from Andrew and our found nonce. Very, very simple. Let's run it. And we're going to iterate through all of the hashes. We're going to really execute some kind of work, and then it's going to tell us that it is valid. Why is that? Because Andrew plus 63,028 gives us a hash that starts with 4 zeros. So basically what we're going to do is we're going to iterate through all of the hashes and found the one that has our unique characteristic. And once again, it's really hard to find that hash, because we spent like 5 seconds on that proof of work function. But it's really easy to validate that hash, because we only run our hashing function here once. And what's more interesting is that if our hash is not valid, for example, I pick 52, and let's run it, our value will not have 4 leading zeros. So our unique characteristic, it's going to be really, really hard for us to guess the right number, because the only right number is actually in our proof of work function. We actually need to either guess it, so we can, of course, pick 63,028 as a random number and just pick it, cheat our way through that proof of work algorithm. But it's really, really hard for us to do it, because we have millions of numbers. And the only number that's going to have, well, not the only one, but the first number that is going to have our 4 leading zeros is 63,028. And that is why our proof of work is really secure. So the only thing that we have is some kind of work and some kind of a function that validates that, and that function should really quickly and easily validate that our nonce, our proof, our answer, so nonce once again is just an answer to our problem, is the right one. And how can we actually use it? So the main usage of that proof of work is nowadays in blockchain, in Bitcoin and Ethereum for now. Ethereum is going to switch to a better algorithm, which is called proof of stake. But yeah, proof of stake is better because we don't spend too much resources. If I'm gonna add like 10 leading zeros or 20 leading zeros, then I'm gonna wait for 10 minutes, for an hour, for 20 hours, for 10 days. And because of the idea that everybody wants to add a block and win that minor reward in Bitcoin, we right now have a lot of electricity consumption on just mining, and that's not alright. Thank you for watching. My name is Andrew. Subscribe to my channel, leave a like, leave a comment, and bye bye.